If I told you we might find life on another planet, using nothing but a thin smear of starlight, would you trust it? Because right now, in quiet rooms lit by monitors, we're watching planets we can never touch. And we're trying to answer a brutally human question: if another world is alive, how would it show itself, without ever speaking? It's early January. Not in a poetic way, in a literal, fluorescent lit way. The kind of morning where the coffee tastes slightly burnt, where your inbox has that New Year, same universe heaviness. Outside the building, the air is cold and metallic. Inside, the air is recycled and warm, and the only weather that matters is happening on a screen. A plot is forming. A spectrum. At first it's almost nothing, just grain. A hiss of numbers, an argument between noise and meaning. Then, slowly, a shape. A dip. Another dip. A pattern that looks like a message that doesn't know it's a message. You and I are here for a reason that's older than astronomy. We want company. We want a future. We want the universe to be the kind of place where Earth isn't a cosmic accident, but a chapter in a longer story. But here's the constraint that makes this search both elegant and terrifying. We can't go there. Not with rockets, not with probes, not with a brave little lander scraping soil into a microscope. These worlds are too far. So far that even our best plans for visiting them are still closer to myth than mission. We don't get rocks. We don't get microbes. We don't even get a photograph most of the time. We get light. A single beam, stretched across space, filtered through an atmosphere that may or may not exist, arriving here altered in a way so small you could hide it inside a rounding error. And we still dare to ask, is it alive? Tonight, because it will feel like tonight by the time we're done, I want to teach you how to read an atmosphere like a detective reads a note. Not a note written in English. A note written in missing colors. And then we're going to confront the most unsettling part: the note can be forged. Because biosignatures, those famous signs of life, can lie. Or rather, nature can mimic life so convincingly that the only honest response is humility sharpened into method. So stay with me. We're going to ride the beam of starlight down to a distant horizon, watch chemistry perform its illusions, and come back with a new kind of hope, the kind that can survive being wrong. Picture the scene that makes this whole field possible. A star sits in the dark like a lighthouse, steady from a distance. Somewhere in front of it, a planet moves, too small to resolve, too dim to see directly, but large enough to block a measurable fraction of the starlight. That moment is called a transit. A crossing. Think of it like watching a moth pass in front of a porch light from a mile away. You can't see the moth's wings, but you can see the light dip. And if you're careful, you can see the way the dip changes with color. Now let's slow the clock and live inside the geometry. The planet isn't a solid disk in the way our minds want it to be. Around the dark circle of its body is a thin ring, its atmosphere, like the edge of a soap bubble catching sunlight. As the planet slides across the star, some starlight schemes through that ring before reaching us. And that light gets interrogated. Not by us, by the molecules in the air. A molecule is a little instrument. It has ways it can wiggle and twist. And when light hits it at just the right color, really, the right energy, the molecule absorbs it, like a piano string vibrating when you sing the right note. So when we spread the starlight out into a rainbow, we don't just see colors. We see absences. Thin dark lines where certain colors have been stolen on the way here. Those missing colors are the planet's atmospheric fingerprint. Or better, a barcode. Scan it, and you can infer what's in the air: water vapor, carbon dioxide, methane, oxygen, ozone, depending on what patterns of missing light you find. Here's why infrared matters so much. In the infrared, molecules are loud. They shout their presence through strong absorption features, because those are the energies that match many of the molecules' vibrations. It's like trying to identify a person in a crowd. In visible light you might get a silhouette, in infrared you can hear their voice. But even with that advantage, the problem is vicious. Small planets are hard. A planet the size of Earth blocks a tiny fraction of a star. And the atmosphere, this delicate ring we're actually reading, adds a signal that's smaller still. We are looking for a few extra atoms worth of shadow. So astronomers make a pragmatic choice. They go hunting around small stars. And dwarfs. Red dwarfs. These stars are smaller and cooler than the Sun, which means an Earth-sized planet blocks a larger fraction of their light. The signal becomes more generous. The transit repeats more often because the habitable zone is closer in. It feels like the perfect shortcut. And yet, this is where the story begins to turn. Red dwarfs can be violent. Active. They flare. They bathe their planets in ultraviolet and charged particles. So the very stars that make the signal easier can make the interpretation more dangerous. Now the word biosignature gets thrown around like a verdict. Like a stamp that says life detected. But a biosignature is not a verdict. It's a clue. It's an atmospheric pattern that, on Earth, strongly correlates with biology. Oxygen O2, ozone O3, methane CH4, nitrous oxide. Sometimes combinations of these. But the most important concept isn't any single molecule. It's chemical disequilibrium. Let me translate that into something you can feel. Imagine walking into a kitchen and seeing a candle flame burning in a sealed jar. Fire needs oxygen. If the jar has been sealed for days, the flame should be dead. If it's still alive, something is replenishing oxygen, or introducing fuel, or opening the jar. Disequilibrium is that feeling. This shouldn't be here, not for long, unless something keeps it going. On Earth, oxygen and methane together are one of those. This shouldn't last. Pairings. Methane wants to react with oxygen. Left alone, they annihilate each other chemically over geologically short timescales. Yet both exist in Earth's atmosphere. Why? Because life keeps pumping them. Plants and microbes and ecosystems are constantly restocking the shelves. So you can see the seduction. If we detect oxygen on another world, especially lots of it, our minds leap. Oxygen on Earth is tied to photosynthesis. Tiny organisms began producing it, and over deep time it transformed the planet. Oxygen became the quiet permission slip for complex life. So in our control room, with our spectrum sharpening, oxygen-like features feel like a clean answer. A simple story: there is oxygen, therefore there are plants, or at least something like them. Now I want you to be in the room at the exact moment that hope arrives. The data pipeline finishes another pass. A colleague leans closer to their screen. Someone stops tapping their pen. The spectrum is now smooth enough to see structure. And there it is, a dip, right where oxygen would leave its mark. Clean. Almost too clean. You feel it in your chest first. That little upward lurch. The brain quietly beginning to write headlines. But then, the most valuable voice in science speaks. Not the loudest one. The most disciplined one. It says, "Before we celebrate, what else can make this?" This is the point where the search for life becomes the audit of reality. Because nature is not obligated to make life the only author of interesting chemistry. Stars do chemistry. Rocks do chemistry. Light does chemistry. And sometimes, chemistry impersonates biology with unsettling skill. So let's stress test the signal. Let's treat it like evidence in a courtroom where the universe is allowed to be clever. First suspect, photochemistry. Photochemistry is what happens when light doesn't just illuminate a world, it edits it. Ultraviolet photons carry enough energy to break molecules apart. They're like tiny hammers that can shatter chemical bonds. Now imagine a planet with water vapor high in its atmosphere. UV light hits those water molecules, H2O, and splits them. Hydrogen, being light and fast, can escape to space. It's like steam leaking out of a pot through a pinhole. But oxygen is heavier. It lingers. It accumulates. Over time you can build an oxygen-rich atmosphere not because anything is breathing, but because the planet is slowly losing its water to space and leaving oxygen behind like ash. This is a nightmare scenario if you're desperate for a simple oxygen equals life rule. Because in this case oxygen doesn't mean forests. It means loss. It means a world that might have been wet once and is now drying out under the glare of its star. So here's a thought experiment to keep us honest. If you saw oxygen on a planet orbiting a violent red dwarf, one that flares and blasts UV, would that increase your confidence in life? Or would it decrease it, because UV-driven water loss becomes a plausible alternative? Second suspect, the aftermath of a runaway greenhouse. A runaway greenhouse is what happens when a planet's climate crosses a line and then can't find its way back. Oceans evaporate, water vapor rises, and water vapor itself is a greenhouse gas, so it traps more heat, which evaporates more ocean. A feedback loop that doesn't negotiate. Think of it as climate tipping into freefall. In that state, the upper atmosphere fills with water vapor. UV splits it. Hydrogen escapes. Oxygen remains. So a planet can look oxygen-rich in a snapshot, while being utterly sterile. The oxygen is not the breath of life. It's the fingerprint of a catastrophe. And that word, snapshot, matters. Because we take single moments and try to infer deep history. Life is dynamic. Planets evolve. But our measurements are like looking at one frame of a long film and trying to guess the entire plot. Third suspect, the famous oxygen plus methane combo. When people first hear oxygen and methane together, it sounds like the universe is waving a banner. Because on Earth, biology supplies both. But can geology do it? Volcanoes release gases. Deep mantle chemistry can generate methane in some conditions. Impact events can inject reducing gases. Serpentinization, when water reacts with certain rocks, can produce hydrogen and potentially methane. Now place that geology under a star with a particular UV spectrum. Change the atmospheric pressure. Add or remove oceans. Suddenly the reaction rates shift. The lifetime of methane changes. Oxygen production pathways change. Is it likely to mimic Earth perfectly? Maybe not. But not likely is not the same as impossible. So we ask the brutal audit questions: could rocks do it? Could sunlight do it? Could the planet's history do it? If you change one assumption, gravity, temperature, ocean coverage, does the biosignature survive? Or does it evaporate like a mirage when you walk toward it? Fourth suspect, the star itself. This one feels unfair because it's not the planet cheating, it's the lamp above the stage. Stars have spots. Dark regions, cooler than the surrounding surface. They have faculae too, bright patches. The surface is mottled, active, alive with magnetism. When a planet transits, it doesn't block a perfect, uniform light source. It blocks a textured, changing star. And that texture can imprint features into the spectrum that look exactly like atmospheric absorption. Imagine trying to read ink on paper while someone keeps changing the color temperature of the light bulb overhead. The ink hasn't changed. The lighting has. But your eyes can be fooled. This is stellar contamination, when the star's own spectral features masquerade as the planet's atmosphere. So another test: what do we know about the star? Not vaguely, precisely. Its activity cycle. Its spot coverage. Its UV output. The very thing we're using as a backlight is also a source of systematic illusion. Fifth suspect, the hardest villain. The one nobody wants to blame because it points back at us. Instruments. Systematics. Wishful thinking. Detectors have quirks. Pixels drift. Temperature changes in a telescope can cause subtle trends. A data reduction pipeline makes choices: how to correct noise, how to subtract backgrounds, how to fit baselines. And if you've ever watched a human mind fall in love with an answer, you know the danger. We don't falsify by accident. We confirm by accident. We nudge. We smooth. We select. Not out of dishonesty, out of hunger. A pattern appears, and our brains do what they evolved to do: they turn it into a face in the clouds. So the scientific discipline here is almost moral. We build blind analyses. We compare pipelines. We inject fake signals to see if we can recover them. We ask independent teams to reproduce results. We demand that a detection survives not just one clever plot but every reasonable way of processing the data. Because if the universe is allowed to be chemically creative, we must be methodologically ruthless. Now comes the pivot, the part where the story could become cynical, but doesn't. Because the answer isn't give up on biosignatures. The answer is context is king. A molecule is not a verdict. It's a character in a larger story. And that story includes temperature and pressure, because chemistry depends on the rules of the room. It includes clouds and hazes, because a high-altitude haze can mute features and make one molecule imitate another. It includes the star's spectrum, because photochemistry is driven by the colors of light a planet receives. It includes planetary mass and gravity, because those decide what gases a world can hold onto and for how long. So we stop asking, did we see oxygen? And we start asking, what kind of world would produce this whole pattern across many wavelengths, consistently, under the star it orbits, with the climate it should have, and the history its orbit suggests? That's the eureka. Not a single line in a spectrum. The realization that life is not a molecule. Life is a system. And if we're going to find it across interstellar distance, we have to detect the system's footprint, not just one exciting ingredient. Let's make it visceral. Picture a forensic board on the wall. Minimalist, clean. Not a conspiracy wall, an evidence wall. Strings connect clues: water vapor here, carbon dioxide there, a hint of ozone, a pressure estimate, a temperature profile, cloud models, stellar UV measurements. Each clue alone is ambiguous. Together, they begin to constrain reality. They begin to corner the truth the way multiple witness testimonies corner a timeline. Now I want to run one more stress test with you, because it changes the way you hear every headline from now on. Time. We tend to imagine planets as static balls with permanent atmospheres. But atmospheres breathe on geological time. They change with volcanism, impacts, escape to space, and if present, biology. So what if we catch a planet in a weird phase? A transitional era. A post-ocean epoch where oxygen lingers. A pre-life epoch where methane is high. A post-impact haze that mimics organic chemistry. You can do everything right and still be looking at a world mid-sentence. That's not failure. That's the honest shape of knowledge at cosmic distance. And here's where the search becomes bigger than finding aliens. Because this is also a lesson in how we know anything we can't touch. It's a lesson in inference. In humility. In the difference between a clue and a conclusion. We're not only hunting life. We're learning how to read the universe without pretending it owes us clarity. So when you hear biosignature, hear it the right way, a hypothesis with error bars. A proposal. A carefully argued suspicion. And the path forward, this is where the future starts to glow, is converging evidence. Multiple molecules detected across multiple wavelengths. Seasonal variability. Does a gas rise and fall as the planet orbits, like Earth's carbon dioxide breathes with hemispheric seasons? Better stellar characterization. Can we model the star's spots and flares so they can't impersonate a planet? Constraints on planetary mass and radius so we know whether it's rocky or gaseous. And eventually, direct imaging, actually separating a planet's light from its star's glare, like picking out a firefly next to a floodlight. That's difficult on a level that borders on absurd. But absurd things have a history of becoming routine in astronomy. Now let's turn the telescope around, emotionally. Let's aim it at us. If aliens observed Earth from far away, would they always recognize it as living? Not necessarily. For most of Earth's history, oxygen was not abundant. Life existed, but the atmospheric signature we fetishize today, the oxygen-rich sky, was absent. Imagine an alien civilization observing Earth 2.5 billion years ago. They might see methane. They might see haze. They might see a world that looks chemically strange, but not obviously alive by our modern standards. Or worse, imagine they observe Earth during a time of enormous volcanic outgassing, or after a massive impact. They could misclassify us. They could file Earth under interest in chemistry, unclear biology. That realization should do something to your sense of certainty. It should make you gentler with the data, and more respectful of how hard this is. And yet, here's the emotional beat I don't want to lose: this search is still worth it. Because every false positive is not just a disappointment. It's a lesson. It teaches us the universe's repertoire. It teaches us how planets fail, how they change, how they lose their oceans, how stars sculpt their skies. And in the process, it teaches us something about Earth that no patriotic speech can, that our planet's balance is not guaranteed by the laws of physics. It's an outcome. A rare arrangement of history and chemistry and time. So when a new spectrum arrives in January, and the room goes quiet, and a dip appears where oxygen would be, the right response isn't cynicism. It's disciplined wonder. It's the willingness to say, I want this to be life, but wanting is not evidence. And then to do the hard, beautiful work of ruling out the other stories the universe could be telling. Let's synthesize what we've learned cleanly. We can detect atmospheres by watching starlight pass through a planet's thin atmospheric ring during a transit, and reading the missing colors like a barcode. We call certain patterns biosignatures, because on Earth they correlate with biology, especially gases that coexist in chemical disequilibrium. But those same patterns can be generated without life, by UV-driven photochemistry, by ocean loss and runaway greenhouse histories, by geological processes under certain conditions, by contamination from the star's own modeled surface, and by the most human culprit of all, instrumental and analytical bias. So the key is not charisma, one exciting molecule. The key is context and convergence, a whole planetary story that holds together across chemistry, climate, and time. Now a contemplative takeaway, something to carry with you after the screen goes dark. Imagine you receive a letter from someone you love, but it has been soaked in rain, smeared, and copied 100 times. You can still recognize certain words. You can even feel their voice in the rhythm. But if you're wise, you don't build your entire future on a single readable sentence. You look for consistency. You look for patterns across pages. You ask what else could have made that mark. That's what we're doing with planets. We're reading rain-soaked letters written in light. And that opens the next great question, the one that should make you slightly uncomfortable, because it's the frontier. If biosignatures can be forged by stars and rocks and sunlight, what would a truly unforgeable sign of life look like? Would it be a pattern over time, like metabolism written as seasonal rhythm? Would it be a combination of gases so fragile that only an active biosphere could sustain it? Would it be something we haven't even imagined because we're trapped in Earth's vocabulary? If you want to think like an auditor of the cosmos, here's your small assignment the next time you see a headline that says, "We found life." Ask, what alternatives were ruled out: geology, photochemistry, the star, the instrument, and what context supports the claim? Now, 2 quick things, and I'll let you go back to your own January morning. First, tell me in the comments, in one sentence, which possibility you find more unsettling: false positives that mimic life, or false negatives where life is present but invisible to our methods. Second, if you want to stay with this journey, subscribe, not for hype, but for rigor. Because the next videos are about building better tests, not bigger headlines. And when this ends, click the end screen video, keep the session going, because the deeper you go, the more the universe starts to feel like a place you can actually read.